Hi, this is Professor Fernandez, and this is video 5 in lesson 13. We're still talking here about critical points and the increasing decreasing tests. So this is really just another example 4.12 from Calculus Simplified, to help you get comfortable with these concepts. So I am going to go a little faster in this video than I did in the previous one. This is video 13.4. So I encourage you to go over there where I talked a little bit more in detail about the increasing decreasing test, what critical numbers are, how you find them, and then how you use this theorem to piece together the information that you're getting from those two things. So I'm just going to follow here this increasing decreasing test. First step is to determine the critical numbers, and then second to plot them on the number line. So the critical numbers we find by finding the derivative of the function. So this is x to the 2/3. Its derivative is 2/3 x to the minus 1/3, power rule, minus the derivative of x, which is 1. Okay, so this is 2 over 3 third root of x minus 1. So that's the derivative. And now we do two things. We set it equal to 0, and we figure out where the derivative does not exist. So setting it equal to 0 is probably going to be the simplest thing to do here. So I do 2 over 3 times third root of x minus 1 equals 0. So I would move over the 1. 2 over 3 third root of x equals 1. Then I would cross multiply, so 2 equals 3 times third root of x. Divide by 3, 2/3 equals third root of x. And then to solve for x, I'm going to cube the whole thing, so I get 2/3 cubed equals x. Why was I cubing? Well, because this is x to the 1/3. And then property of exponents, I cube everything, gets rid of 1/3. So x equals 2/3 cubed. That is 2 cubed is 8. 3 cubed is 27. So 8 over 27 is my x value, where the derivative is 0. Great, that is my only critical number for that part. These are sometimes called stationary points. Now I want to find where the derivative does not exist. In this example, we do have such values because look at the derivative. It has an x down here, x to the 1/3. So x cannot be 0. That would make the derivative undefined. So that gives me x equals 0 as another critical number. So I have two critical numbers, 0 and x over 27. So what I'm going to do next is plot these on the number line. That's the last part of this first step in the increasing decreasing test. Okay, so let me just clean things up here so I have enough space to plot things on the number line that I need plotted. Okay, so draw my number line. So I have 0 and I have 8 over 27. And it's always a nice idea to put f prime of x over here because in the increasing decreasing test, we are going to be substituting in values in between these two x values into the derivative. So I have three parts of the number line that I want to substitute in values. Like we've talked about before in this video, doesn't matter which values you substitute in. You really just want to pick ones that will make evaluating f prime of x simple. So here are some values that we could choose. How about we choose 1 over 27 to be in the middle here, and I'll show you why I chose that in a minute. But we choose 1/3 to be over here, let's see. Let me think a little bit. So we choose 1. Let's keep the 1 over 27. I'll show you why I'm hesitating in a second. And then something to the left of 0, how about -1? Okay, so why did I choose 1 over 27? Well, as I said earlier, you want to pick values that help you evaluate f prime of x quickly. The f prime of x that we have has a x to the 1/3 in the denominator. So we would like to choose something that we can find x to the 1/3 for pretty quickly. And that's why I chose 1 over 27 here. 27 is 3 cubed. So f prime of 1 over 27 would be 2 divided by 3 times 1 over 27 to the 1/3 minus 1. Okay, so 1 over 27, this is 1 over 3 cubed to the 1/3. So once again, those 3's here go away. 1/3 times 3 is 1. And then these 3's go away. 3 over 3 is 1. So I get 2 over 1 minus 1 equals 1. So positive. All right, so for 1 over 27, I put a plus in my sign chart. In other words, the derivative is increasing at that point and between these two numbers. So now let's look at f prime of 1 over here. So f prime of 1, this one's much simpler. This x to the 1/3 becomes 1 to the 1/3. That's just 1. I get 2/3 minus 1. That's negative. I'm not really keeping track of the number here. It doesn't matter. So negative. So I put that in my sign chart. And then let's look at f prime of -1. f prime of -1. I get 2 divided by 3 third root of -1 minus 1. The third root of -1 is -1. So I get minus 2/3 minus 1. That's less than 0. So I put a negative here on my sign chart. Okay, let me clear up the clutter, and then we can finally interpret what is happening. So this is where this theorem 4.1 comes in. That's over here on the lower right. What does the theorem say? So if I zoom in a little bit, the theorem says, suppose the function is differentiable on some interval. If the derivative is positive on that interval, then the function is increasing on that interval. If the derivative is negative on that interval, then the function is decreasing. So I'm going to go back up here. So then I'm going to say function, maybe write f of x here. Because it's negative, the derivative is negative, the function is increasing. Because the derivative is positive here, then the function is decreasing. Because the derivative is negative here, the function is increasing. So you can get some sense of, oops, I messed that up. Sorry, because the derivative is negative, the function is decreasing. And because the derivative is positive, the function is increasing. Because the derivative is negative, the function is decreasing. I had in my head the previous example that we did in video 13.4. So that's why I wrote down the initially wrong directions. Okay, so negative derivative, function decreasing. Positive derivative, function increasing. Negative derivative, function decreasing. Great, so now you can kind of sketch out what the function looks like. You know, you could trace these out. And we're expecting a graph of the function that looks kind of like this. You know, has a valley here and a hill here, if you want to think of it that way in terms of its graph. So I've graphed the function over here. And you can see that, you know, the graph is not exactly what we sketched out. That's why it's a sketch, right? But we do have this decrease. And then we have this now increase over here. And then we have this decrease. And these are the points, right? This is x equals 0, and this up here is the 8/27 that we found. So it doesn't look as smooth and flowy as what we've just drawn. It looks more like it goes down and then comes up and then goes this way, right? But again, this is a quick little sketch based off of the first derivative test that helps us get some sense of how the function increases and decreases without having to graph it. Remember, as I keep saying in this video series, this lesson in particular, when calculus was invented, we did not have calculators or computers. We couldn't graph functions just, you know, quickly by, you know, pulling up Wolfram Alpha on your computer or using some other applet. So calculus was kind of it, you know, it was all we had. So even being able to give this insight into how the function increases and decreases was a really important advance to helping us understand functions and how they change. Okay, so that's it for this video. Thanks for watching.